The difference between a circular orbit and the true orbit could be distinguished only by precise measurement and a courageous acceptance of the facts. Quote, "The universe is stamped with the adornment of harmonic proportions, but harmonies must accommodate experience." Unquote. Kepler was shaken at being compelled to abandon a circular orbit and to question his faith in the divine geometer. Eventually, Kepler came to feel that his fascination with the circle had been a delusion. The Earth was a planet, as Copernicus had said, and it was entirely obvious to Kepler that the Earth, racked by wars, pestilence, famine, and unhappiness, fell short of perfection. Kepler was one of the first people since antiquity to propose that the planets were material objects made of imperfect stuff like the Earth. And if planets were imperfect, why not their orbits as well? He tried various oval-like curves, calculated away, made some arithmetical mistakes, which caused him at first to reject the correct answer, and months later, in some desperation, tried the formula for an ellipse, first codified in the Alexandrian library of Apollonius of Perga. He found that it matched Tycho, who was another famous astronomer. He found that it matched Tycho's observations beautifully. So I thought that was very interesting about that needed change in worldview. And even Kepler saying a very radical thing, that experience must trump our speculations, and that our theories must conform to experience. You're going to find even today in certain realms of thought that experience or not, we don't care about experience, we care about the theory only. This must be true. But Kepler was one of the first scientists to say that no, experience is so important that it must trump even astronomy, even religion. So of course Galileo also was very important in that as well. Probably more important than Kepler, but still, it was still very. It was a risk. It was a risk to use experience to deny or to reject religious truths, and even consider the idea from Plato that our senses are imperfect and we could be being deceived. And that also, a lot of religious doctrine and metaphysics is based on Plato. It's often called Neoplatonic. And that also had an effect on what science could do, that science could not simply go from experience, that they also had to deal with the objection that, oh, but your senses are just deceiving you, that kind of stuff. That idea of theory before experience. So this is just something interesting. This is on page 49. It says that unlike the orbits of Mercury and Mars, the orbits of the other planets depart so little from circularity that we cannot make out their true shapes even in an extremely accurate diagram. Just kind of an odd fact. So perhaps no wonder it was hard for them to move off the circle. But of course, still Mars screwed with them, because Mars and the backing up in the orbit really messed up their calculations. And just another point about Kepler, this is on page 51. Magnetism is, of course, not the same as gravity, but Kepler's fundamental innovation here is nothing short of breathtaking. He proposed that quantitative physical laws that apply to the Earth are also the underpinnings of quantitative physical laws that govern the heavens. It was the first non-mystical explanation of motion in the heavens. It made the Earth a province of the cosmos. Astronomy, he said, is part of physics. Kepler stood at a cusp in history. The last scientific astrologer was the first astrophysicist. So for the longest time, of course, there were astrologers, very much in the sense of the newspaper astrologer, with the Cancer and Pisces and all that stuff, having some impact on this world. Because for the longest time, it was believed that there's two worlds. There's the heavens and the earth, and there's separate universes, separate existences. And the things that happen in this world, even the laws that happen on this world, are not at all relevant, certainly not the same, not at all relevant to the heavens. The heavens is a whole other thing. And it was Kepler, I guess, as they're saying here, the first astrophysicist to say that, oh no, actually, we are not, the Earth is not just some separate thing, and the heavens some separate thing, or the cosmos some separate thing. The Earth is a province of the cosmos. They're both under the same laws. And so again, there's this decentering and this breaking down of the religious worldview, the dualism, probably from Plato. The dualism of two universes going on, that this earth is our prison and pain and things like that, and the earth is the cloud, is the blue sky, is the heaven, is the place where we want to be. And we would like to go up there, kind of thing. We'd like to rise up to the heavens, kind of thing. But no, Kepler, in his observations, was the first to break away from that astrology and to say, no, we're not being looked down upon by gods. Out there is just the same as down here. And this is, again, destroying this dualism and creating a monism throughout the world. That the physics and the laws that happen here are similar out there. And this isn't some special place, and up there isn't a special place. It's all the same existence. So that's another massive worldview change. So more stuff on Kepler. It was an interesting guy, of course. It says here that he wrote the first works of science fiction, and he intended it to explain and popularize science. It's very interesting because a lot of people have done it in the last couple hundred years. Like, for example, Francis Bacon. Of course, he was older than a couple hundred years ago, but all kinds of these scientists that produce these works of science fiction in order to popularize it. It was called Somnium, which is the dream, and it's about imagining a journey to the moon and space travelers standing on the lunar surface and observing the lovely planet Earth rotating slowly in the sky above them. That's apparently what the book was about. That's on page 52. On the next page, another point from Kepler, he says that because of the length of the lunar day and night, Kepler described the great intemperateness of climate and the most violent alternation of extreme heat and cold on the moon, which is entirely correct. So apparently the moon must spin very slowly to have a very lengthy day and night, right? That's based on the spin of the planet. So if it spins very slowly, you're going to see the sun longer. Now, what's the consequence of seeing the sun longer? Not only is it also that you see the sun even more slowly when you're turned around and the sun's behind you, but also the sun is heating up this side of the earth for a lot longer. And you're cooling a lot longer when you're behind, and you're behind the sun, or the sun you don't have daylight, it's nighttime. That's a massive consequence, of course, because you're heating up and getting really, really hot, and then you're cooling for a long time as well. Those extremes in temperature are not conducive to life. It's conducive to cracking of the surface and all kinds of damage. And essentially, it really harms stability. Having this heat, this oven turning on, being thrown in the oven and then thrown in the freezer, like that you can't live in that kind of thing. Plants can't live, animals can't live, and even bacteria may have a hard time. So it's saying here that because of the spin on the moon, no wonder it looks as it does. But I guess then we're lucky on planet Earth that our spin is sufficiently fast that we have a decent amount of sunlight and warmth, and then we can have a cool down period at nighttime, and then repeat. So that spin speed is important. On the next page, on 54, Johannes Kepler believed that there would one day be celestial ships with sails adapted to the winds of heaven, navigating the sky filled with explorers who would not fear the vastness of space. And today those explorers, human and robot, employ as unerring guides on their voyages through the vastness of space the 3 laws of planetary motion that Kepler uncovered during a lifetime of personal work and ecstatic discovery. I just thought that was a great quote, that Kepler's laws and his predictions about sailing the winds of heaven would also translate into exactly what we do now with spaceships and all that. So now something about Newton. So we're just soon out of Newton and Kepler, but this is on Newton. This is on page 56. Newton, in his mid-40s, was described by his servant as follows: I never knew him to take any recreation or pastime, either in riding out to take the air, walking, bowling, or any other exercise whatever, thinking all hours lost that were not spent in his studies, to which he kept so close that he seldom left his chamber unless to lecture at term time, where so few went to hear him, and fewer understood him, that oft times he did, in a manner for want of hearers, read to the walls. I thought that was interesting about Newton. And then just continuing down more in astronomy, it says, the moon, it seemed to Newton, would fly off in a straight line, tangential to its orbit, unless there was some other force constantly diverting the path into a near circle, pulling it in the direction of the earth. This force Newton called gravity, and believed that it acted at a distance. There is nothing physically connecting the earth and the moon, and yet the earth is constantly pulling the moon toward us. So let me just stop for a second here. So, of course, if something is moving, why doesn't it just move in a straight line? If it's got momentum and it's moving, something is curving its movement as opposed to it just moving straight off. Something is curving its movement, so it's being caught, almost as if there was a string around the moon, and we're just pulling it around. Or actually, not even that. The moon has momentum, but its momentum is being blocked, or it's certainly being influenced, and it can't move off in a straight line, but instead it has to move around this gravity well that we have, I guess. But the metaphor is about like a string being wrapped around the moon, and it can't move straight off, but it instead just can move. It's used its momentum against that resistance and has to move around. And so Newton was looking at this, and he was like, how is this possible? Any other object would just move straight off if it had no other impediments. But something is impeding the moon and causing its movement, its momentum, to actually make it curve. And so what is this? Well, there's no physical linkage, but it must be something else. So we call this thing gravity. So now I'll continue. And yet the Earth is constantly pulling the moon toward us. Using Kepler's third law, Newton mathematically deduced the nature of gravitational force. He showed that the same force that pulls an apple down to Earth keeps the moon in its orbit and accounts for the revolutions of the then recently discovered moons of Jupiter in their orbits about that distant planet. Things had been falling down since the beginning of time. That the moon went around the Earth had been believed for all of human history. Newton was the first person ever to figure out that these two phenomena were due to the same force. So, again, that's just another story about Newton and gravity. And again, this decentering of this getting away from the idea that the heavens are something different, and another connection being made, that the gravity that makes an apple fall down here is the same gravity that's keeping the moon around us. So it's another idea of laws here are the same as laws up there. And so I think this is a final conclusion quote about Newton and Kepler. It's on page 58. Kepler and Newton represent a critical transition in human history, the discovery that fairly simple mathematical laws pervade all of nature, that the same rules apply on Earth as in the skies, and that there is a resonance between the way we think and the way the world works. They unflinchingly respected the accuracy of observational data, and their predictions of the moon, of the planets, to high precision provided compelling evidence that, at an unexpected deep level, humans can understand the cosmos. Our modern global civilization, our view of the world, and our present exploration of the universe are profoundly indebted to their insights. So I thought this was very interesting because, again, it seemed this is very Aristotelian, not from Plato. Plato was not a help in this process. It was Aristotle, especially with the idea of the respect of accuracy of observational data. This is definitely an Aristotelian idea. This is why Aristotle is considered the father of science, not Plato, because Plato was one who would reduce the accuracy, even need for observation, and instead depend much more heavily on theory and even metaphysics, just as religions do today. Less likely to look at observation. And even the Bible itself, you notice that the Bible is becoming more and more allegorical, not literal. Again, that's a Platonic idea of we have this worldview that we're defending against observation. And you can get into, of course, the whole thing about observation being part of the body, and the body is less than the mind. The mind is the theory. The body is fallen, or it's like the Christian view of the fallen world, that kind of stuff. That it's debased and all of that. So again, this is a very Aristotelian pursuit of science and combating religious metaphysical views and theory as to what the world must be, especially this view of humans as the earth as egocentric and humans as the best in the universe and things like that. And this decentering of that as, no, what's really going on is we're just on this lonely planet and there's no dualism. It's the laws of nature here, the laws of nature out there. So again, this is a profoundly, this is a bashing of that, I guess at that point, very nice picture that was being painted of what this reality is.